I believe that all of us have heard many times about the relevant role that the environment plays in the sustainability assessments of products, and in fact it is relevant. However, less has been talked about the role that the social dimension of sustainability plays in such assessments. This communication aims to show how the inclusion of social interests in life cycle assessments might lead to significantly different results with respect to those obtained from conventional two-dimensional approaches. This is the overview of this presentation, which is quite conventional, by the way. We will first go through a brief introduction, then we will talk about the research methodology, then I will present the results obtained from the study, and at last we will describe the most relevant conclusions that can be drawn. Finally, some relevant references will be provided for those of you that might be interested in reading more about this topic. The conventional approach for the design of infrastructures, such as bridges, consists of finding that particular geometry that best fits the budgetary restrictions existing at the time of constructing the structure, while complying with the requirements of strength and functionality requested by the existing codes. During the last decades, the scientific community has put great effort in the analysis of the economic impacts throughout the entire service life of structures, thus assessing structural designs from a life cycle perspective. Indeed, maintenance has revealed itself as a critical source of economic impacts along time, conditioning thus the design of infrastructures in maintenance-demanding environments. However, life cycle assessments from an economic perspective are not enough. The recently established Sustainable Development Goals claim for a paradigm shift in the way structures should be conceived. In recent times, research has been conducted on the evaluation of the environmental impacts associated to the service life of infrastructure. The inclusion of this dimension in the economic assessments has allowed designers to find solutions that fit better the sustainable future that the society demands. However, an adequate sustainability design requires the simultaneous consideration of each of the three dimensions on which sustainability relies, which are not only economy and environment, but also society as well. But to date, less attention has been paid to the assessment of the social impacts related to the design of infrastructure. This communication aims to analyze how the inclusion of social aspects in the life cycle sustainability assessment of bridges in coastal environments can condition both the selection of materials as well as the maintenance strategies to be followed, leading to more sustainable solutions if compared to those obtained through conventional assessments. This study focuses on a prestressed concrete bridge deck located in Galicia, in Spain. This bridge is located in a coastal environment and has a continuous box girder deck, as you can see in the figure. The baseline design, which is called as ref hereafter, is assumed to have a passive reinforcement amount of 100 kg per cubic meter, with a concrete cover of 40 millimeters. This baseline design is based on a concrete mix with a cement content of 350 kilos per cubic meter of concrete and a water to cement ratio of 0.4. Besides to this reference or baseline design, 6 alternative designs are studied here which provide better durability performance in chloride-laden environments, as the one assumed here. As a first alternative, the water to cement ratio of the reference concrete mix is reduced from 0.4 to 0.35, so as to increase the concrete cover resistance against chloride diffusivity. Other alternatives are evaluated where particular materials are added to the baseline design, to the baseline mix. These alternatives consist of adding 10% silica fume, 20% fly ash, or 10% latex. The durability of concrete structures in coastal environments can also be improved, obviously, by using corrosion-resistant steels, So here a design alternative considering stainless steel reinforcement is analyzed. At last, the performance of hydrophobic surface treatments applied to the deck surface is also evaluated. This table shows the concrete mixes considered for each design. It shall be noted that the concrete mix for the alternatives inox and hydro is the same as the baseline mix. This analysis is a life cycle-oriented study, which considers as a functional unit a 1 meter long section of the bridge deck under study over a 100 years time span. A gate-to-grave life cycle approach is assumed here, including the impacts that result from every activity required to guarantee a 100 years long service life of the deck. Therefore, the system under analysis covers from the resource extraction and production of the different construction materials associated to each design alternative under evaluation, up to the demolition activities at the end of the life of the bridge. The system under analysis also includes the maintenance activities required by each of the alternatives depending on their durability performance against chlorides. To evaluate the advance of the chloride front in concrete over time, a two-dimensional version of the Fickian model proposed in FIP Bulletin 34 has been used. The particular values of the durability parameters of each design alternative are given in the table shown here. On the basis of these values, the failure probability at any time can be evaluated by means of Monte Carlo simulations, considering that failure occurs when the chloride concentration exceeds the critical chloride content at the depth of the river. Maintenance is considered here to be mandatory, always that the reliability reaches the limit reliability. Here, a limit reliability of 1.3 has been considered. Maintenance can be optimized by finding those intervals below this limit interval, which result in life cycle sustainability responses that are maximized. For the impact assessment of the economic dimension, two impact categories have been considered, which are the costs during construction of the bridge deck and the discounted maintenance cost over time, which will be dependent on the maintenance demand. In this assessment, a social discount rate of 2% has been chosen to discount maintenance costs. The environmental dimension has been assessed by using the recipe 2008 methodology. This methodology considers or translates 18 midpoint indicators into 3 endpoint indicators that are simpler to interpret. Those endpoint indicators are considered here as the 3 impact categories assumed for the impact assessment, which are damage to human health, damage to the ecosystems, and depletion of resources. The social dimension has been assessed using or following the methodology proposed by Navarro et al. In 2018. This indicator-based methodology considers 4 social impact categories associated to bridge infrastructures here in Spain, which consider the workers and the generation of employment, the economic development of the regions as a result of the economic investments in the different production centers, the impact on the users of the bridge deck, that means travel delays or reduction of travel safety resulting from maintenance activities, and at last, the public opinion. To perform the life cycle analysis, data has to be gathered in a phase that is called the inventory analysis phase. The environmental data has been obtained from the EcoInvent 3.2 database, combined with a specification of manufacturers associated to the different energy demand and performance of the machinery involved in the different activities. The social data has been gathered directly from the Spanish Tax Office and the Spanish National Statistics Institute. And at last, the economic data has been obtained from construction-specific databases. The sustainable design of infrastructures can be considered a multi-criteria decision-making problem. In this case, the TOPSIS methodology has been used to assess sustainability. This methodology seeks for the solution that lies closer to the positive ideal solution, while being simultaneously sufficiently far away from the worst solution. In addition, in this case, the relevance of each criterion has been obtained by means of the analytic hierarchy process, the AHP. So now we will talk a little bit about the results obtained. First of all, I would like to talk about the relevance of each criteria. A group of experts has been consulted to determine the weights via AHP to be associated to each criterion by using this technique. Two cases have been studied, namely the two-dimensional and the three-dimensional approach, each of them providing different criteria weights. Those weights are shown in those two tables presented here. So what about the life cycle results of the first two-dimensional approach, which would be a conventional approach nowadays? It is observed that the preferred design is the alternative hydro. This has resulted in the best life cycle performance, both in the environmental and in the economic dimension individually. Although it requires to be reapplied every 5 years, it is a very competitive alternative in terms of costs. In addition, this reapplication does not require from the production of additional concrete for the replacement of the concrete cover. So it results in very low environmental impacts. On the contrary, the worst life cycle performance is that one associated to the baseline design. Such design shows bad durability and results in excessive maintenance demand along the analyzed 100-year service life. Such demand results in great environmental impacts resulting from the material needs, as well as in great economic costs associated to each maintenance activity. Here you can see the results of the proposed three-dimensional approach, which includes the social dimension. Here we can see that in this case the preferred solution is the one based on the use of silica fume. On the contrary, the reference or the baseline design continues being the worst solution. So if we consider the three sustainability dimensions simultaneously, it shall be observed that the design performing best along its life cycle is the one based on the use of concrete with silica fume, as we have seen before. This solution, although scoring less than the design based on hydrophobic surface treatments on the economic and environmental assessments individually, has a much balanced response when adding the social dimension. Consequently, the sustainability score of this design is 11% greater than the sustainability score of the alternative hydro, which was the best according to a conventional design, a conventional approach. The need of a periodical reapplication of surface treatments every 5 years incurs in negative social impacts on the public opinion and the aesthetics of the bridge sites and also on the infrastructure users, thus resulting in bad social scores that can be observed in the figure here. On the contrary, the maintenance-free alternative based on the use of stainless steel results in the highest social scores, as the public opinion and the users of the infrastructure are benefited from the structure to remain unaffected along its entire service life. From the results observed in the three-dimensional approach, it is observed that the optimum maintenance interval for some of the designs has changed when adding the social dimension in the assessment. In particular, it is observed that these optimal intervals have increased. This is due to the fact that the social positive impacts on users and on the public opinion are benefited from reduced affection of the structure along time. At last, we will have a look at the main conclusions of this study. The main conclusion would be that conventional two-dimensional sustainability assessments of structures based on the sole consideration of the economy and of the environmental impacts are not enough to properly catch the holistic scope of sustainability. So when including the social dimension in life cycle assessments, it results in optimum maintenance intervals that are increased if compared with the conventional approaches. It is observed that solutions with less maintenance are encouraged, and that solutions might increase significantly the sustainability response along time. In this case, we have observed that the solution with silica fume has a sustainability score of up to 11% greater than the best alternative resulting from a conventional approach. So at last, we would like to acknowledge the financial support of the Spanish Ministry of Economy and Competitiveness, which has supported this study and this research. And here we have included some references that we consider to be relevant if you might want to read a little more about this topic. So thank you very much for your attention.